My name is Jonathan Dodge. I'm a Senior Applications Engineer at United Silicon Carbide and one of the developers of FET-Jet Calculator. This video explains at a high level how FET-Jet Calculator works. As mentioned in the FET-Jet Calculator overview video, FET-Jet is a calculator based on steady-state circuit analysis and data from device datasheets. To model power losses in a circuit, we must first understand how the circuit works. So a behavioral simulation is extremely useful for this. I like to use PSIM. So let's look at a single phase of a two-level voltage source inverter as an example. Using sine triangle modulation, a fundamental frequency sinusoidal modulating signal is compared with a switching frequency triangular carrier signal to create the pulse width modulation signals that control the gates of the two FETs in the half bridge. The AC output voltage is the voltage across the load, which in this case is a resistor and inductor in series, referenced to the center point of the DC link. In a three-phase inverter, this may be an imaginary point. In the simulation results, the phase current, which is the inductor current, is scaled to be about the same amplitude as the modulating signal to make it easy to plot them together. And here you can see the lag between the phase current and the modulating signal, which the modulating signal is in phase with the output voltage. Current flows through Q1 in the positive direction during one half of the cycle, and in the negative direction, defined as current flowing into the half bridge during the other half of the fundamental cycle. So during the forward conduction portion, the Q1 has switching loss, and then in the reverse conduction portion there's no switching loss because it's functioning as a synchronous rectifier. So we will calculate the average conduction loss and average junction temperature, for ignoring the minute details of the circuit operation. Forward conduction loss is it's calculated as I squared R, so current squared times resistance. We're going to use a switching function, which is 1 whenever the modulating signal exceeds the carrier signal, and it's 0 otherwise. Now we'll make some simplifications and integrate, and the results of the integrating allow us to replace this modulating function with the switching function replaced with a modulating function. And so we're ignoring the effect of current ripple, we are ignoring dead time, and we are considering the ratio of switching a fundamental frequency to be very large. So we ignore the effect of finite number of pulses within the line cycle. We end up with closed form equations, which are very convenient to use. They are with respect to modulation index and the phase angle phi. We have an equation for the forward conduction loss, and then a similar process is used to find the reverse conduction loss. And we calculate the switching loss. First we take the switching loss data from the data sheet, adjust it to the operating temperature, and then we apply a second order curve fit to it. We take the coefficients, put them in the equation, integrate over a line cycle, or fundamental cycle I mean, and we end up with, again, a closed form equation for the average switching loss over that full cycle. Turn on loss is calculated the same way as turn off loss. And we have losses versus temperature. Here we take into account the temperature dependence of RDS on with temperature, and we put that into the equation for temperature rise based on power loss. So RDS on is dynamically updated as you use the calculator. So this was a very quick overview. I hope you find it useful, and I hope that you enjoy using the calculator. Thanks for watching.